Okay, in 2.27, we are given a double delta potential well, and we're asked to do a number of things. Part A, we want to sketch this potential. So this is pretty easy to do. We just have to recognize that there's two delta wells here. Everywhere else, when x is equal to anything other than positive or negative a, this is just going to equal to 0. So let's write this out in a more sort of revealing piecewise function. So v of x is going to equal, and it's going to equal 0 when x does not equal a, or let's do plus minus a. If x equals a, then this argument equals 0, and this thing becomes infinity. So this becomes negative alpha Dirac delta x minus a when x equals a. And then when x is negative a, then this Dirac delta has an argument of 0 and becomes prevalent, whereas this one just goes to 0. So this becomes negative alpha Dirac delta x plus a when x equals negative a. We just have to sketch this. So let's say that this is x equals negative a, and this equals x equals positive a, in which case our Dirac deltas, we have two peaked around negative a and positive a, so it's going to look something like this, and then we do a similar peak at positive a. And that is our graph for part A. Okay, in part B, we're asked how many bound states it possesses for two cases, for two different values of alpha. Before we even get into the second part, we're going to start by recognizing the fact that we're working with bound states. So in part B, bound states means that the energy is negative. And if the energy is negative, and also if we recognize that effectively we're dealing with three regions, right? We have x is less than negative a less than x less than positive a, and x is greater than a. And if we recognize that we're basically looking at these three regions separately in the same way that we did for the single delta potential well with bound states, then what we're going to do is we're going to recognize that v is effectively always equal to 0 in all three regions. So our Schrodinger equation sort of reduces to the case we defined at the start of the delta function well chapter, where we were doing when we actually analyzed bound states for the single potential well, which is that d2 psi by dx squared is going to equal negative 2me divided by h bar squared times psi. And then we can redefine this as just k squared times psi, where k is going to equal the square root of negative 2me divided by h bar. And once again, the reason why we're defining k this way with a negative square root is because of the fact that sort of e is negative, so the negative that is internal in the e cancels out with the negative at the front of the 2. And I messed up this fraction a little bit, apologies. Anyway, if we do this, then the resulting solution is going to take on the form of exponentials. So psi, in fact, let's write out the full piecewise function for psi now. Psi is going to equal three different sets of exponential solutions, a e to the negative kx plus b e to the positive kx when x is less than negative a. We have ce to the negative kx plus d e to the kx when x is between negative a and positive a. And we have e times e to the negative kx plus f times e to the kx when x is greater than a. And if you don't remember how to solve this sort of differential solution, go back to the section video, which where we actually go through this derivation in detail. Anyway, next we sort of have to introduce some conditions, because if we look up at the x equals negative a area, x is going down to negative infinity. So this term is fine because this term is going to go to 0 as x goes to negative infinity. But this term sort of isn't fine because of the fact that at x equals negative infinity, this becomes a e to the power of positive infinity, which means that this term blows up. And that's not allowed, because if we have a term that goes to infinity in our wave function, then it's not going to be normalizable, which automatically breaks every rule that we've set up so far. So by sort of by the requirement that psi can't blow up to infinity, we're going to assume that a is equal to 0 here and cancel this out. This problem doesn't happen between negative a and a because this is a finite region, so neither of these terms blow up to infinity. In the x is greater than a region, similarly, for the same reason, we have to cancel out, we have to require that f equals 0 because of the fact that if it didn't, then e to the kx would blow up to infinity and x equals infinity, and therefore we would once again be stuck with an unnormalizable function. So more realistic or more simplified, our piecewise solution becomes a piecewise of b e to the power of kx when x is less than negative a, c e to the negative kx plus d e to the kx when x is between negative a and positive a, and then e times e to the negative kx when x is greater than a. And let me just move this top one over so that everything matches up nice and easy. Okay, this is our wave function. Our goal is to find the number of bound states it possesses. And in order to do that, we have to start by sort of solving out all of these constants at the front and getting a full wave function first before we can actually do anything. So automatically, we have to do the exact same process we did back in the actual section, which is we have to create a system of equations in order to solve for b, c, d, and e. To do that, we have two different sort of scenarios that allow us to assign sort of conditions. So the first case is continuity of psi. So what this means is that the wave function has to be continuous. There can't be any jumps. So what we can do is automatically at x equals negative a, these two have to equal. So we have be to the negative ka has to equal ce to the positive ka plus de to the negative ka. And what I'm doing here is I'm defining x equals negative a, and I'm requiring the fact that at this negative a joining point, these two wave functions have to equal each other. Similarly, we do the same thing for the middle and bottom function at x equals positive a, which is going to give us that ce to the negative ka plus de to the ka must equal e times e to the negative ka. So there's condition 1 and 2. The next two conditions we can get via sort of the discontinuity, the derivative of psi. So discontinuity in d psi by dx when v is infinite. We also sort of derived out what this is going to be in the chapter itself, so look back if you don't remember how to do this. But the basic rule is that the difference in sort of the derivative of psi, delta d psi by dx, at some critical point, which let's call like x equals a, for example, is, or in fact, let's just say x equals plus minus a, is going to equal negative 2m alpha divided by h bar squared times psi of plus minus a, respectively, where plus and minus a are the 2 points on our graph where the potential does go to infinity, because remember, these are sort of the centers of our delta wells. So if we plug this in, then what we're going to get is immediately, first off, we have to derive psi. So d psi by dx is going to equal, we just take derivatives of this. This is going to be b times k e to the kx, negative ck e to the kx plus dk e to the kx. I just realized I didn't include the negative at the front here. E to the negative kx times dk e to the kx, and then we have negative e k e to the negative kx. So this is when x is less than negative a, this is when x is between negative a and positive a, and this is when x is greater than a. We can move this down in order to sort of use this as a reference. So the difference in the derivative is equal to this. So let's do this for our two cases where x is negative a and x is positive a. So when x is negative a, we have the final minus initial. So negative ck e to the, this is when x is negative a, so negative kx becomes positive ka plus dk e to the negative ka. Subtracted by the final minus initial. So this is fine. This second term is final. This first term is initial. So initial is going to be bk e to the negative ka. And this is going to equal negative 2m alpha divided by h bar squared times psi at negative a. So we can choose to either use this or this, because remember, they both equal each other at negative a. For simplicity's sake, it's better if we just use this one, because this one only has one term, whereas this one has two terms. So let's define this b times k e to the negative ka. Or actually, I apologize, that we want psi at negative a, not d psi by dx at negative a. So psi at negative a is going to be just b e to the negative ka. So let's do this, and then b times e to the negative ka. I apologize for that. Okay, next one, at x equals positive a, the discontinuity in the derivative is going to be final, which is negative e k e to the negative ka, because this time we're plugging in at x equals positive a, minus initial, which is going to be the middle term, so this is going to be plus ck e to the negative ka minus dk e to the ka, where we reverse all the signs at the front here. And this is going to be equal to negative 2m alpha divided by h bar squared, and then psi at positive a, which we're going to say, for simplicity, once again, is going to be the bottom term, because there's only one here, whereas the ce to negative kx plus d to the kx has two terms. So this is going to be e times e to the negative ka. Just double check that that's correct. Negative ka, b, negative ka, yes. Okay, and these are sort of our four conditions. So let's just move them down so that they're all next to each other and nice and tidy. And next, we're going to solve this system of four equations for our four variables, because we have b, c, d, and e, which is four variables, and we have four equations. So we just have to sort of, it's kind of tedious, but we kind of just have to sort of plug and chug our way through this. So we will do that now. Okay, so remember that our final goal is to find, our goal is to find e. And since e is directly related to k, this implies that we want to find k. So what we're going to do, effectively, is we need to sort of solve these one by one to eliminate corresponding variables until finally we're left with only one variable, and we can just eliminate it from the resulting equation. So we can do this, there's multiple ways to do this, depending on how you prefer to solve systems of equations. I'm going to do this more systematically. I'm going to start by just getting rid of all of the b terms by solving this first equation in terms of b. So let's do that. Step 1, solve equation 1 for b and plug into everything else. So let's do that. We have b e to the negative ka is equal to ce to the positive ka plus de to the negative ka. If I want to solve this for b, I just multiply everything by e to the positive ka. This is going to give me b is equal to ce to the 2 ka plus d. So then I just take this and I plug it in to sort of equations 2, 3, and 4, and I just forget about equation 1. So if I do that, then we have sort of the same equation. For equation 1, it stays the same because there's no b term. So ce to the negative ka plus de to the positive ka is equal to big E times e to the negative ka. Next, we have negative ck e to the ka plus d k e to the negative ka minus, and here we have a b, so we want to start substituting them. So this is going to be, let's see, minus k e to the negative ka times b, which is going to be ce to the 2 ka plus d, and this is going to equal negative 2m alpha divided by h bar squared times e to the negative ka multiplied by b again, which is going to give us ce to the 2 ka plus d. Similarly, for the bottom equation, we're going to get negative e k e. Actually, the bottom equation doesn't change at all because there's no b's here either. So plus ck e to the negative ka minus d k e to the ka is equal to negative 2m alpha divided by h bar squared e times e to the negative ka. And actually, I'm going to, so first off, I'm going to sort of collect all these in a bracket to emphasize that they're part of a set. And now I'm going to do some reorganizing. So this is the painful part of this problem, which is that everything kind of sucks here because of how complicated this system is and how tedious it is. More realistically, if you're ever doing this, I would heavily recommend you to just plug these systems of equations into like Mathematica to do this. But unfortunately here, since I'm determined to do everything by hand, I just have to sort of suffer through this. So next thing we're going to do is the second step, which is we're going to solve equation 1 again, and let's solve these variables in order. So let's solve equation 1 this time for C and plug into everything else. So if we do that, what we're going to get is, let's see, CE to the negative KA is going to equal negative DE to the positive KA plus E times E to the negative KA. The second and third terms I'm going to rearrange, or I'm going to fully expand out first before rearranging a little bit. So this is going to be negative CK e to the positive KA plus DK e to the negative KA minus CK e to the KA, yes, and then minus DK e to the negative KA, and this is going to equal negative 2m alpha divided by h bar squared e to the negative KA, or sorry, I want to distribute this out, so if we're writing in the same format as we've done before, then C times e to the positive KA this time, because negative KA times positive 2KA, and then subtracted by 2m alpha divided by h bar squared d e to the negative KA. Okay, so that's this second equation fully expanded. Let's do the same. Let's reorganize this a little bit on the third side. So this is going to be CK e to the negative KA minus DK e to the KA. I'm going to collect like terms and move the e to the other side. So this is going to be EK e to the negative KA minus 2m alpha divided by h bar squared e times e to the negative KA. Okay, once again, we group everything, and now we start the next step, which is to solve for C for this equation, and then we also want to sort of collect like terms on both sides here and sort of distribute out some stuff. So let's start with the first equation. Let me just take a sip of water real quick. Okay, so we're going to multiply both sides by e to the positive Ka, so it's going to be C is equal to negative D e to the 2Ka plus E. So this is equation 1. Next, let's move all the C's to one side and all the D's to the other side for equation 2. So negative C K e to the Ka minus, in fact, we can just combine these two terms and say this is going to be negative 2. Negative 2 CK e to the Ka plus 2m alpha over h bar squared C e to the Ka is going to equal, and I'm going to move everything else over. So first off, these two terms automatically cancel out because it's dk e to negative Ka, negative dk e to negative Ka, which actually makes our lives a lot easier. This is going to just be equal to negative 2m alpha divided by h bar squared d e to the negative Ka. Onwards to the final one, this one is going to give us ck e to the negative Ka minus dk e to the Ka is going to equal e times e to the negative Ka multiplied by k minus 2m alpha divided by h bar squared, right? E to the negative Ka, k minus 2m alpha divided by h bar squared. Yes, okay, and this is our new set. And now we move on and do this whole thing all over again. So now for step 3, solve equation 1 for, or actually no, we haven't finished step 2 yet. I'm sorry. We still have to plug this in to like sort of these two equations. So let's do that first. So what that's going to give us is negative 2 k e to the Ka multiplied by C, which is negative d e to the 2Ka plus E. And actually, you know what? In fact, I'm going to make this even simpler on myself by distributing out the C first before I do anything. So I'm going to rewrite everything first. So we have sort of the same equation here that I'm just going to copy paste. And then we have, let's see, CE to the KA multiplied by negative 2K plus 2M alpha divided by H bar squared. Is that correct? CE to the KA, negative 2K plus 2M alpha divided by H bar squared. Yeah, this is equal to negative 2M alpha divided by H bar squared. DE, oops, that looks like a P. DE to the negative KA. And instantly, I see that I can cancel out a 2 to make my life a little bit easier. So I'm going to do that. And the bottom term remains unchanged. Okay, and now this is my actual fully simplified set of 3 equations. I need to extend my canvas a little bit, so let's make this 10,000. There we go. Okay, now we plug this in. So this is going to be, let's see, E to the KA times negative K plus M alpha divided by H bar squared. And then multiplied by C, which is going to give us negative D, E to the 2KA plus E. And this is going to equal negative M alpha divided by H bar squared times D, E to the negative KA. And then we have K times E to the negative KA multiplied by C, which is going to give us negative D, E to the 2KA plus E, minus DK, E to the KA. This is going to give us E times E to the negative KA multiplied by K minus 2M alpha divided by H bar squared. And this is now a set of 2 equations. And now let's fully expand this out. So let's see, I'm going to start by just combining this fraction into a single fraction. This is going to be negative K H bar squared plus M alpha divided by H bar squared. Let's just move the negative to the front, to the top here, just to emphasize, to not make confusion. Let me just double check that that's correct. Negative K H bar squared plus M alpha divided by H bar squared, yeah. And then E to the KA times negative D, E to the 2KA plus E. And this is going to equal negative M alpha divided by H bar squared, D, E to the negative KA. And immediately, let's see, I can cancel out the H bar squared at the bottom of everything and make my life slightly easier. So I'm going to do that. Add parentheses at the front here. Move this down. Move this down. Whoops. I do not want to do that. I want to move it down like that. There we go. Okay, next, let's distribute out this. So this is going to be negative dk e to the ka, I believe. Yes, and then plus ek e to the negative ka minus dk e to the ka equals e times e to the negative ka times, and I'm going to combine this as well, so k h bar squared minus 2m alpha, all divided by h bar squared. And this is our new set of 2 equations. Now let's fully sort of distribute this out. So this is going to give us, let's see, negative d e to the 3ka. Is that correct? Yes. Negative d e to the 3ka times negative k h bar squared plus m alpha. And then plus e times e to the ka times negative k h bar squared plus m alpha. And this is equal to negative m alpha d e to the negative ka. And then at the bottom we have, let's see, negative 2 dk e to the ka equals e to the negative ka times k h bar squared minus 2m alpha, all divided by h bar squared, minus k e to the negative ka. I'm just moving the e to the right so that we collect all the like terms. What does that leave us with? If we simplify this even more, then what we're going to get is, let's see, negative d e to the 3ka times negative k h bar squared plus m alpha plus m alpha d e to the negative ka is equal to negative e times e to the positive ka times negative k h bar squared plus m alpha. And then on this side we have negative 2 dk e to the ka is going to equal e times e to the negative ka times k h bar squared minus 2m alpha divided by h bar squared subtracted by k e to the negative ka. And in fact, I don't know why I'm not just distributing out the e to the negative ka in the first place. And then let's move this over to here and do this. Okay, kind of getting a little bit painful here, but nonetheless, we have to keep moving on. Our next step is this, what step are we on? This is, yeah, so on step 3, solve equation 1 for D and plug into equation 2. So, God, this is horrible. It's going to be D times negative e to the 3ka times negative k h bar squared plus m alpha plus m alpha e to the negative ka. This equals negative e to the ka times negative k h bar squared plus m alpha. So then D is going to equal negative e to the ka, and then negative e 3ka negative k h bar squared plus m alpha e to the negative ka at the bottom, and then this is a fraction, so this is going to become negative k h bar squared plus m alpha. Okay, this looks horrible. Let me see if there's a way for me to maybe make this a little bit better. We can multiply e to the ka to the bottom, so in that case D is going to equal negative e, and then let's see, negative e times, so if we want to multiply this by 1 over e to the, or instead of doing that, let's just multiply e to the negative ka over e to the negative ka to get rid of the e to the k at the top. Then it's going to give us negative e to the 2ka negative k h bar squared plus m alpha, and then plus m alpha e to the negative 2ka. Is that correct? Yes, it is. Okay, and let's make the fraction, and then this is going to be negative k h bar squared plus m alpha. Okay, now we plug it in. So this is going to give us, let's see, negative 2k e to the ka, and then multiplied by our D term, which is equal to this horrible mess of a thing. Close off this bracket, and it's going to equal e times e to the negative ka times k h bar squared minus 2m alpha over h bar squared, and I'm going to combine this fraction, so it's going to be minus k h bar squared over h bar squared. Yeah, okay, and now so immediately we can cancel out the negative along with the e, because those are like terms. That instantly means I can move everything over a little bit, thank God. Okay, let's do this. Let's see, 2k e to the ka, and then negative e to the 2ka, k h bar squared plus m alpha e to the negative 2ka, and then negative k h bar squared plus m alpha, is equal to e to the negative ka, and I'm going to simplify this fraction, so the kh bars cancel. This one cancels with this one, so what we're left with is just negative e to the negative ka times 2m alpha divided by h bar squared. Okay. Let's see. Apologies, I just realized I made a bit of a mistake in the math here. When I'm going down here on this final step, I sort of left out the negative sign in front of the kh bar squared earlier. So now we have to redo this all over again and fix our mistake. Let's see, this is going to give us negative k squared h bar squared plus km alpha. This is equal to negative e to the negative 2ka times m alpha divided by h bar squared, and then multiplied by negative e to the 2ka, negative k h bar squared plus m alpha e to the negative 2ka. From here, let's distribute in the negative e to the negative 2ka, so negative k squared h bar squared plus km alpha is going to equal m alpha over h bar squared multiplied by, so these two make 1, so negative k h bar squared plus m alpha, and then subtracted by m alpha e to the negative 4ka. And this is sort of very obviously a transcendental equation. So what we're going to have to do later is we're going to have to plug in the conditions for alpha, because if we look back in the instructions, we have that we want to solve it for two cases where alpha equals h bar squared over ma and h bar squared over 4ma. So what we're going to do later is we're going to plug in alpha and we're going to graph out the equation on Desmos and try to find valid solutions for k. But before that, let's do a little bit more simplification. Negative k squared h bar squared plus km alpha is going to equal, let's see, negative km alpha plus m squared alpha squared h bar squared minus m squared alpha squared over h bar squared e to the negative 4ka, in which case negative k squared h bar squared plus 2km alpha is equal to m squared alpha squared over h bar squared 1 minus e to the negative 4ka. Okay, so now that we have the actual condition for k, there's two different hypotheticals that we want, because if we think back to part B, we want to find the allowed energies for, in case 1, alpha equals h bar squared over ma, and in case 2, alpha equals h bar squared over 4ma. So now it's just a matter of plugging these into this equation for k, and then finding the allowed values for k, and then after that, since k is directly related to energy, finding the allowed values for energy. So let's start with case 1. So we have, in this case, negative k squared h bar squared plus 2km multiplied by alpha, which becomes h bar squared over ma. And this is going to equal m squared over h bar squared multiplied by alpha squared, which is going to be h bar to the 4th over m squared a squared times 1 minus e to the negative 4ka. And from here, we can start doing some simplification. Negative k squared h bar squared plus the m's cancel, so we have 2k h bar squared over a. Is that correct? 2k h bar squared over a, yeah. And then the m squareds cancel, h bar squared cancels h bar 4th, h bar squared over a squared, if that's, yeah. Multiplied by 1 minus e to the negative 4ka. Then we realize we can cancel out all the h squared, so we have negative k squared plus 2k over a is equal to 1 over a squared, 1 minus e to the negative 4ka. Or, if we want to move the a squared over to this side, then we have negative ka squared plus 2ka is equal to 1 minus e to the negative 4ka. Now, this is very obviously a transcendental, so what we're going to have to do from this point is basically go on Desmos and graph this out and see for what values of k this relation is true. So what we can do is we're going to move everything to the right, so what we get is then 1 is equal to 1 minus e to the negative 4ka divided by negative ka squared plus 2ka. Next, we do the same thing for alpha equals h bar squared over 4ma. So for case 2, what we're going to get is, let's divvy this off here. Oops. we have negative k squared h bar squared plus 2km times alpha, which is going to be h bar squared over 4ma. This is going to equal m squared over h bar squared times alpha squared, which is going to give us h bar to the 4th over 16m squared a squared, multiplied by 1 minus e to the negative 4ka. From this point, let's do some simplification again. Negative k squared h bar squared plus the m's cancel, 2 and the 4 cancel. We have k h bar squared over 2a, I believe. Yes, okay. And then this is going to equal the m squareds cancel out. We have h bar squared over 16a squared multiplied by 1 minus e to the negative 4ka. Same as before, the h bar squareds cancel. We have negative k squared plus k over 2a is equal to 1 over 16a squared times 1 minus e to the negative 4ka. From this point, we multiply the 16a squared over to the left. We have negative 16ka squared plus, let's see, this is 8ka, and this is equal to 1 minus e to the negative 4ka. Once again, a transcendental, so we move everything to the right and graph this on Desmos. This is going to give us 1 is equal to 1 minus e to the negative 4ka divided by negative 16 times ka squared plus 8ka. And these are effectively the two conditions we have for k in these two scenarios where alpha equals h bar squared over ma and h bar squared over 4ma respectively. So now it's just a matter of plugging this into a computer and getting numerical values for the energy. Okay, I'm not going to go through plugging this into Desmos because that's just a pretty easy thing to do. Regardless, in each of these scenarios, we're going to get different values. So it turns out for this left side, we're going to get that Ka has two valid solutions. It equals either 0.797 or 1.109. And on the right side, Ka also has two valid solutions, negative 0.628 and 0.369. For this one, since Ka, or K more specifically, because A is just a positive constant, K is equal to square root of negative 2me over h bar squared, or over h bar, I believe. Hang on, let me double check this. Yes, okay, yeah. So K is equal to square root of negative 2me over h bar. A is just some positive constant. So the problem here is that K can't become negative. This is not a valid solution, because if this equals some constant, well, E is by definition negative for a bound state. So this top term must be positive. Same thing, h bar is just a positive constant. So it has to be a positive constant. It cannot equal a negative constant. So automatically, this solution is just not valid. So what we have left are these three possible values. We plug this into, this equation, and we get the corrected values of energy. So we have 0.797, let's make it a set. 1.109 times is equal to Ka, which is equal to A times the square root of negative 2me divided by h bar. So in this point, if we want to separate E, we just solve this algebraically and get the value for E. Same thing over here. We have 0.369 is going to equal Ka, which is going to equal A times square root of negative 2me divided by h bar. And with that, we're done with this part of the problem. And now we have to move on to the significantly harder part, which is to sketch the wave functions, because this will actually involve having to take this, take the wave function we've defined so far, this piecewise right here, and basically redefining all the coefficients so that there's only one coefficient here. And then after that, we have to sort of we have to normalize everything in order to get an actually valid wave function. And since we have three different possibilities via two hypothetical scenarios of different values of alpha, we have to do this 3 times. So this is very painful, and I will begin this as soon as I cut. Okay, so to recap, in part B, we want to find how many bound states each sort of system possesses in the two hypotheticals of two different values of alpha. We have found the different values allowed for Ka, and therefore the different values allowed for energy. In case 1, we have 2 possible bound states. In case 2, we only have 1. The next thing we want to do is we want to sketch the wave functions. To do that, we have to take our general wave function, which was this piecewise we defined earlier. And the first thing we have to do is we have to redefine everything in terms of only one constant so that we can actually do normalization later on. And that involves sort of all of these definitions of B, C, and D. So we're going to convert everything into E and rewrite this. So this is obviously very painful. Let's do this. So we have, let's see, psi is going to equal, and we're going to start by doing the B conversion. So this is going to be, let's see, e to the kx times ce to the 2ka plus d. And let's see. Yeah, so this is, I'm just going to leave that as this. And then we have ce to the negative kx plus de to the positive kx. And then we have e to the negative kx. For our three conditions. Next, let's convert C. So this is going to equal e to the kx, and then we have e to the 2ka multiplied by C, which is going to give us negative d e to the 2ka plus e. And then we're adding d. And then at the bottom here, this is going to be e to the negative kx multiplied by negative d e to the 2ka plus e. And we're adding d e to the kx. And then we have e times e to the negative kx. So here, let's do some reorganization. Let's see. This is going to give us, for the top one, e to the kx as before. We're just going to put that on the outside always. Negative d e to the 4ka plus e times e to the 2ka, and then we're adding d to this, and then we have e to the negative kx, d e to the 2ka plus e plus d e to the kx, and then we have e times e to the negative kx. So we can rearrange this a little bit. This is going to become e to the kx times d multiplied by 1 minus e to the 4ka plus e times e to the 2ka. Okay, and now is the hard part. So I'm going to give me 1 second as I rearrange all my work to make this a little bit neater, and then we will work on this final substitution going from d to e. Okay, now let's plug everything in. So psi is going to equal, we have e to the kx, and then this horrible thing. So this is going to be negative e times negative k h bar squared plus m alpha multiplied by 1 minus e to the 4ka divided by negative e to the 2ka times negative k h bar squared plus m alpha plus m alpha e to the negative 2ka, and then we're adding e times e to the 2ka. And then we have, on the bottom side, e to the negative kx multiplied by negative e times negative k h bar squared plus m alpha times e to the 2ka, all divided by negative e to the 2ka negative k h bar squared plus m alpha e to the negative 2ka. And then we're adding an e term at the front. And then we add de to the kx. So actually this is minus, let's see, e times negative k h bar squared plus m alpha multiplied by e to the kx, all divided by negative e to the 2ka times negative k h bar squared plus m alpha e to the negative 2ka. And then finally, at the bottom, we just have e times e to the negative kx. Okay, this is a pretty disgusting looking piecewise. Let's try to simplify this a little bit. What can be done to make this a little bit easier? So first off, I'm going to distribute out the e. So we have e times e to the kx multiplied by And then maybe I'm going to put the negative in. So this is going to be kh bar squared minus m alpha times 1 minus e to the 4ka divided by e to the 2ka times kh bar squared minus m alpha added with m alpha e to the negative 2ka. And then we're adding e to the 2ka. And then for the middle one, we can once again distribute out the e. So this is going to be e times e to the negative kx. And then do the same thing, kh bar squared minus m alpha, where we absorb the negative that's here. And then multiplied by e to the 2ka. And then at the bottom, once again, do the absorption e to the 2ka times kh bar squared plus minus m alpha plus m alpha e to the negative 2ka. And then this is getting added to 1. And then we subtract e to the negative kh bar squared plus m alpha e to the kx divided by e to the 2ka kh bar squared minus m alpha plus m alpha e to the negative 2ka. And you know what? In fact, I'm just going to change this to a positive and move the negative, or sort of rearrange the negative here. Minus m alpha. And then at the bottom, we just have e times e to the negative kx. Okay, this middle term looks like it could be simplified a little bit more. Let's see. No, actually, it might not be able to. Yeah, okay, no, maybe not. Unfortunately, because of the fact that they don't share a common e to the kx factor, or negative kx factor, I can't do easy cancelization or combining here. Okay, this is tentatively, for now, our piecewise function purely in terms of e. Now we have two cases, so let's start with case 1, where alpha equals h bar squared over ma. And let's plug this in and let's see what happens. So in case 1, what we're going to get is psi being equal to, let's see, e times e to the kx. And you know what, since this is, before I even do anything, it might be better to actually take this factor. So we have e to the 2ka times kh bar squared minus m alpha plus m alpha e to the negative 2ka, all divided by kh bar squared minus m alpha. So this is a common term that appears 3 times. So kh bar squared minus m alpha e to 2ka, kh bar squared minus m alpha plus m alpha e to negative 2ka. Same thing here as well. Yeah. Okay, so this is a common factor that appears 3 times. So it might be easier to just redefine this with alpha before we do anything else. So this is going to be kh bar squared minus m times h bar squared over ma. And then we have e to the 2ka times kh bar squared minus m times h bar squared over ma plus m times h bar squared over ma times e to the negative 2ka. If we simplify this, this is going to give us, let's see, e to the 2ka over kh bar squared minus h bar squared over a plus h bar squared over a times e to the negative 2ka. And then this is all divided by kh bar squared minus h bar squared over a. We can multiply a over a, so there's nothing stopping us from multiplying a over a in order to make this a little bit nicer. So what's this going to give us? This is going to give us ka h bar squared minus h bar squared, all divided by e to the 2ka times ka h bar squared minus h bar squared plus h bar squared e to the negative 2ka. We can cancel out h bar squares. We get k, okay, yeah, that becomes e to 2ka times ka minus 1 plus e to the negative 2ka, and then at the top we get just ka minus 1, which is very convenient. So this is a nice little simplification. Let's take this and move it down. So psi is going to simplify itself a little bit, and it's going to become e times e to the kx, and then multiplied by 1 minus e to the 4ka, which doesn't change, and then this simplified expression. So actually, you know what, it might be easier to just write everything as a single fraction. So this is going to become e to the 2ka times ka minus 1 plus e to the negative 2ka, and then this is divided by ka minus 1 multiplied by 1 minus e to the 4ka. And then this is added with e to the 2ka. So that's our first term. Now our second term, this is e times e to the negative kx. And this is going to give us e to the 2ka, ka minus 1, plus e to the negative 2ka at the bottom. And then at the top, we're going to get, what is this? Let's see, ka minus 1 times e to the 2ka. Yeah. Which is added with 1. And then we add e times ka minus 1 e to the kx divided by e to the 2 ka minus 1 plus e to the negative 2ka. Okay, yeah, that's the middle term, and then the final term is just e times e to the negative kx. So this is for the case of 1. And now we start plugging in, because we have these two conditions that ka equals these two. So what we really have is, let's do this 1a is going to be that psi equals, let's see, e times e to the kx times 0.797 minus 1 times 1 minus 4, or 1 minus e to the 4ka divided by e to the 2ka. Or in fact, yeah, these just all become numbers. So this is gonna be, oh god, okay, this is gonna be very painful to write out because of the fact that it's all numbers. 4 times 0.797, and then we're dividing this by e to the power of 2 times 0.797 times 0.797 minus 1 plus e to the negative 2 times 0.797. And this is getting added with e to the 2 times 0.797. And then for the middle, this is e to the negative kx, and then, oh god, 0.797 minus 1, e to the 2 times 0.797 divided by e to the 0.797 times 0.797 minus 1 plus e to the negative 2 times 0.797 plus 1 plus e times 0.797 minus 1 e to the kx divided by e to the 2 times 0.797 times 0.797 minus 1 plus e to the negative 2 times 0.797 for the middle, and then at the bottom just e times e to the negative kx. Okay, I am going to compute these now, and I will be right back. Okay, these are my final results after plugging in all of the numbers. I very likely did something wrong, and it is very easy to do something wrong here. I have no doubts that I probably will have done something wrong at some point in all of this calculation, and this is probably going to end up becoming some nonsensical wave function that isn't actually continuous. But at this point, really, this is more just like trying to emphasize the method for solving and less actually physically solving. I can't imagine anybody would ever go through the trouble of doing something like this by hand in a standard setting. So really, what I'm just trying to emphasize through this problem, how to actually do this, how you would actually go through and do this. I'm going now to normalize all of this, and if it works, great. If it doesn't, that's unfortunate. It'll mean that I did the problem wrong. However, the general method is still right. So if you had something like this on a test and you did it my way, I would expect that it would be reasonable for you to get at least 80% on this problem, because numerical answers really, getting the actual correct answer is not very important. What's important is actually knowing how to do the problem itself. So now that we have this, let's actually normalize this. So first off, we have Ka, right? We have the fact that Ka equals 0.797 here. So we have Ka equals 0.797. So what that means is that K itself is equal to 0.797 over A. So if we substitute that in, then what we're going to get is that psi is equal to negative 0.154 times e to the 0.797 over a times x, when x is less than negative a. And then when between negative a and positive a, we have 2.255 times e to the negative 0.797 over a times x, plus 0.255 times e to the 0.797 divided by a times x. And this is when x is between negative a and positive a. Let me just double check my work to make sure that's right. Yes. And then we have e times e to the negative 0.797 over a times x when x is greater than a. Okay, at this point, we're going to do normalization now. So we have the requirement that the magnitude of psi squared has to, integrated from negative infinity to positive infinity, has to equal 1. So what this tells us is that, let's see, 0.154 squared times e squared times the integral. In fact, you know what? I'm just going to distribute out all of the e's to make this a little bit easier on myself. I'm going to write this as e squared multiplied by 0.154 squared integral from negative infinity to negative a of e to the 2 times 0.797 divided by a times x dx, plus 2.255 squared integral from negative a to positive a of e to the negative 2 times, negative 2 times 0.797 divided by a times x, and then plus e to the 2 times 0.797 divided by a times x dx. Is that correct? No, apologies. I didn't realize that I thought they were both 2.255, but one of them is 0.255. So actually, we close off this dx first, and then we add 0.255 squared integral from negative a to a times, actually, wait, this is just straight up wrong. I'm sorry. What this is actually supposed to be is, let's see, the integral from negative a to positive a of 2.255 e to the negative 0.797 over a times x, plus 0.255 e, the e has been distributed out, e times 0.797 over a x dx, and we're squaring this, and then finally we're adding just e squared, so there's a coefficient of 1 at the front, so this is from positive a to positive infinity of e to the negative 2 times 0.797 divided by a x dx. And now we just have to do each of these individually and equate the final result to 1. So let's start with the first one. So number 1, integral from negative infinity to negative a, e to the 2 times 0.797 divided by a times x dx. So 2 times 0.797, if I plug that into my calculator, is going to give me the integral from negative infinity to negative a of e to the power of 1.594 divided by a times x dx. And this is going to give me, let's see, a divided by 1.594 times e to the 1.594 over a times x, going from negative infinity to negative a. And that's going to give me, let's see, a divided by 1.594 multiplied by e to the negative 1.594 minus e to the negative infinity, which is just 0. So this is going to be a over 1.594 times e to the negative 1.594. If I plug that into my calculator, e to the negative 1.594 divided by 1.594, that's going to give me 0.127 multiplied by a. Next, we're going to do number 2, which is the integral from negative a to positive a of 2.255 e to the negative 0.797 divided by a times x plus 0.255 e to the 0.797 over a times x squared dx. So this one is going to equal, let's see, 2.255 squared e to the negative 2 times 0.797, so negative 1.594 over a times x, and then plus 2.255 times 0.255. Let's see, this one times this way, and then just 1, so yeah, and then we're multiplying it by a 2 at the front, and then we're adding finally 0.255 squared e to the positive 1.594 over a times x dx. Okay, let's see, what are these going to give us? 2.255 squared is just going to become 5.085 multiplied by, let's see, negative a divided by 1.594 times e to the negative 1.594 over a times x. And then we're adding, and then this is, this middle term is 2 times 2.255 times 0.255. This is 1.15, and then we're multiplying by x, because we're integrating this. And then finally, 0.255 squared is going to be 0.065 times a divided by 1.594 e to the 1.594 over a times x dx. No, not dx. Evaluated from negative a to a. So everything here is evaluated from positive a to negative a. Okay. So from here, I want to do some math and cancel out some stuff. 5.085 divided by 1.594. Negative a, oops, no. Negative 3.19 a times e to the negative 1.594 over a times x plus 1.15x plus 0.065 divided by 1.594. This is 0.041 a e to the 1.594 over a times x, evaluated from negative a to positive a. Now let's start plugging in our values. So this is going to be, let's see, negative 3.19a times e to the negative 1.594 minus e to the positive 1.594. And then we have plus 1.15 times a minus negative a, which is going to be a plus a. And then we're going to be plus 0.041a multiplied by e to the 1.594 minus e to the negative 1.594. Okay, now I go into my calculator again. e to the negative 1.594 subtracted by e to the positive 1.594 is going to give me negative 3.19a multiplied by negative 4.72. And we're adding 2a times 1.15. 1.15 times 2 is just going to give us 2.3. And then we're adding 0.041a multiplied by, and then we have this time e to the positive 1.594 subtracted by e to the negative 1.594. This is going to give us 4.72 positive. Okay, add these all together. This is going to give us 3.19 times 4.72. This is going to be 15.057 plus 2.3a plus 0.041 times 4.72. This is going to be 0.194a. Add an a at the front of all of them. Add them all together. So this is going to be 15.057 plus 2.3 plus 0.194. This final value is going to be 17.551a. Okay, and then finally our third one, which is thankfully a lot easier. Let's see, this is the integral from a to infinity of, what was it? e to the negative 1.594 over 8x. dx, and then we just multiply a over 1.594 with a negative in front times e to the negative 1.594 over a times x, evaluated from a to positive infinity. This is going to give us negative a over 1.594 multiplied by e to the, let's see, so what's this going to be? E to the negative infinity is just 0, so 0 subtracted by e to the negative 1.594. That is e to the negative 1.594. That's going to be 0.203. So this is going to be 0.203 divided by 1.594. That is going to give us 0.127 times, and I forgot the a at the front. Okay, now we go back and we add everything together. So this is going to be e squared multiplied by, and then the results of integral 1, which is 0.127a, added with the results of integral 2, which is 17.551a, and then integral 3, which is 0.127a. And this is finally supposed to equal 1. So if we add them all together, then 0.127 plus 17.551 plus 0.127 is going to equal, so this is e squared times 17.805a is equal to 1. E squared is then equal to 1 over 17.805a. E is therefore equal to the square root of 1 over 17.805a, or just 1 over, let's see, the square root of 17.805 is going to give us 4.21 or 4.22 times the square root of a. And now we have our value for e, so we go back to the original sort of setup right here. And if we plug in e for everything, then psi is going to equal, let's see, negative 0.154 times 1 over 4.22 root a times e to the 0.797 over a times x when x is less than negative a, 2.255 times 1 over 4.22 root a times e to the negative 0.797 over a times x plus 0.255 times 1 over 4.22 square root of a times e to the 0.797 over a times x when x is between negative a and positive a. Let's move the condition over here. And then finally, 1 divided by 4.22 square root of a times e to the negative 0.797 over a times x. Now, Let's simplify this a little bit, actually multiply out all of our numbers. So for the first one, we have negative 0.154 divided by 4.22. That's going to be negative 0.036 over the square root of a times e to the 0.797 over a times x. And then we have 2.255 divided by 4.22. That's going to give us 0.534 divided by root a, multiplied by e to the negative 0.797 over a times x, plus, and then 0.255 divided by 4.22. This is going to be 0.06, yeah, 0.06 over square root of a e to the 0.797 over a times x. And then finally, 1 divided by 4.22. This is going to give us 0.237 over the square root of a times e to the negative 0.797 over a times x. This one is for x is less than negative a, between negative a, less than x, less than a, and you know what, I forgot to add x greater than a at the bottom for both of these. And that should be our wave function. So now I'm going to plug this into Desmos, and hopefully it gives me a result that actually makes sense. Okay, so this is the final result. Very obviously it's wrong, because instantly I see that it's discontinuous. Obviously we've made some sort of mathematical error somewhere here, but I think I'm just going to leave it at this, because I really don't think it's worth it to actually go back and comb through everything in order to find like what little arithmetic error I made. Overall, the general method for solving this is correct. So let's review that one more time. And even though we didn't get the correct answer, we can take faith in the fact that the way we're doing this is correct. It's just way too sort of tedious to be worth actually going through the trouble of doing the whole thing by hand. So once again, in part B, what we did was we defined our 4 sort of boundary conditions for this wave function. The first 2 we got from continuity of psi. The second 2 we got from the discontinuity of the derivative of the wave function when the potential is infinite, which is exactly at these 2 potential wells. And then we used those 4 conditions to solve a system of 4 variables, A, B, I think it's B, C, D, and E. We solved this system of 4 equations with those 4 variables, and we eliminated all the variables in order to get a final result, or in order to get a final equation in terms of Ka. So now that we have our final equation in terms of Ka, we solved for Ka in the result. We got 3 valid solutions for Ka, 2 for sort of case 1, 1 for case 2. And then from that point, sort of in order to continue onwards and actually graph the solutions, what we had to do is we had to take the wave function that we had from before, and we had to redefine all of these coefficients in terms of a single coefficient. In this case, we defined them all in terms of E. And from that point onwards, after defining everything in terms of E, we had to normalize everything in order to find what E actually was after plugging in the alpha condition, which we did for condition 1. We could do it again for condition 2, but I'm not going to because it's just way too much work, and also there's something wrong with this. I've done some sort of arithmetic error here at some point, either here or later down below or earlier up above, and it's just not worth it to do it all over again considering how long this video is already. But anyway, we plug in the condition for alpha, we simplify our expression, and then once this is simplified, we plug in the value for Ka, and then after that, we just solve out numerically everything to get a final sort of piecewise wave function purely in terms of one coefficient. We don't have to do it in terms of E. We decided to do it in terms of E here, but realistically you can do it in terms of A or B or C or D or E or F or whatever. And then from that point, we did normalization. We normalized everything, found the actual value for E, got the full numerical solution for psi, and then graphed it. And in this case, we see that we had done something wrong. Something is wrong with our numerical solution. We forgot a negative sign somewhere, or like we didn't write down a multiplicative factor or something like that. Either way, this is a wrong solution, but it sort of follows the general method for solving it. So in my opinion, it's good enough. Okay, now let's do part C, after skipping a bunch of stuff from part B that just really isn't worth going over, considering it's just repeats of the same thing. What are the bound state energies in the limiting cases where A goes to either 0 or infinity, holding alpha to be fixed? And then we're asked to explain why our answers are reasonable by doing comparison with a single delta function well. So
to start off, we're looking at what happens to the bound state energies. So instantly, the thing I think of is sort of the relation we define for k at the sort of in part B. So that relation states that negative k squared h bar squared plus 2k m times alpha is equal to m squared alpha squared over h bar squared times 1 minus e to the negative 4ka. So we're holding alpha to be a constant. Let's look at the first case, which is that a is approaching 0. So in that case, what we're going to get for k is that negative k squared h bar squared plus 2k m alpha is equal to m squared alpha squared over h bar squared times 1 minus e to the power of, now, since a is going to 0, this is just 0. 1 minus 1, this entire thing goes to 0. So what we're going to have left is that negative k squared h bar squared plus 2k m alpha is equal to 0. From this point, we can move our things around a little bit. K squared h bar squared is equal to 2k m alpha. Instantly, we can cancel out a k, so k h bar squared is equal to 2m alpha, or k equals 2m alpha over h bar squared. Next, since ultimately we're looking at the conditions for what happens to the bound energy, we can relate the fact that k equals the square root of negative 2me over h bar. So that means the square root of negative 2me over h bar is equal to 2m alpha over h bar squared. We can cancel out one factor of h bar. What we have left is negative 2me is equal to 4m squared alpha squared over h bar squared. Cancel out a 2, cancel out an m, negative e is equal to 2m alpha squared over h bar squared, or e is equal to negative 2m alpha squared over h bar squared. And that is sort of the first condition where a goes to 0. Now let's look at the second one. Okay, in case 2, a is going to infinity, so what we have is negative k squared h bar squared plus 2k m alpha is equal to m squared alpha squared over h bar squared, and then here we have 1 minus e to the, and let's see, this is going to become negative infinity. So e to the negative infinity is just 0, so this is just going to equal 1. So our condition now is negative k squared h bar squared plus 2k m alpha is equal to m squared alpha squared over h bar squared. From this point, what we have left is sort of a expression for k. So what we can do now is, and in fact, what we have to do now is sort of rewrite this as a polynomial expression. So let's do that. Negative k squared h bar squared plus 2k m alpha minus m squared alpha squared over h bar squared is equal to 0. From this point, we can do a little bit of division, and we can say that k squared minus k times 2m alpha over h bar squared minus, or now plus, m squared alpha squared over h bar to the 4th is equal to 0. Let me just make sure that I did that right. Yes, okay. And from this point, to solve for k, we can use Pythagorean theorem. So we know that a equals 1, b equals negative 2m alpha over h bar squared, and we know that c equals m squared alpha squared over h bar to the 4th. So k is equal to negative b plus or minus square root of b squared minus 4ac all over 2a. So if we want to do this, this is going to give us that k is equal to, let's see, 2m alpha over h bar squared, because this is negative b, plus or minus square root of 4m squared alpha squared over h bar to the 4th, minus 4ac, so 4m squared alpha squared over h bar to the 4th, all over 2a, which is just 1. So this square root term automatically just goes to 0, so there's really only one solution. 2m alpha over h bar squared divided by 2, so times 1/2. This is equal to m alpha over h bar squared. Next, we include sort of the condition that k equals the square root of negative 2me over h bar. And then this is equal to m alpha over h bar squared. So square root of negative 2me is then equal to m alpha over h bar. Negative 2me is equal to m squared alpha squared over h bar squared, or E is equal to, let's see, negative m alpha squared over 2 h bar squared. And this is a little bit messy. Let me just rewrite that. And this is our condition for when a goes to infinity. Okay, finally, we're asked to explain why our answers are reasonable by comparing with the single delta function well. So in the single delta function well case, what happens is we have for single delta well, we have that the energy is just equal to negative m alpha squared over 2 h bar squared. So this, if you look at it, is exactly equal to the a goes to infinity case, and it's sort of smaller by a factor of 4 compared to the a goes to 0 case. So in that way, sort of the fact that all of these energies have the sort of almost the same sort of how do I say this? The fact that all three of these cases have energies that are basically whole number multiples of each other is sort of basically is very encouraging, because that sort of implies that they're related to each other. And if we think about it physically, these two both represent just two single delta wells. So the fact that they are so similar in the fact that they have all the same constants in the same locations, with the only difference being like a multiplicative whole number factor, and that the fact that that factor is even, it's a factor of 4. This energy is smaller than this energy by a factor of 4, so it's an even factor. Is just that those are all just general sort of promising things that we notice that sort of suggest that we actually do have the correct answer. There really isn't anything that goes any deeper than this, honestly, at least in my opinion. Maybe there's some more subtle things that are related. Maybe the factor of 4 is somewhat special, or maybe it's not. Who knows? Either way, we can be reasonably sure that we're, if not correct, then at least on the right track, just because of the fact that sort of the double, the two limiting cases of the double square well energies are basically just whole number multiples of the single delta well energy. And in the case of a going to infinity, it's exactly equal. So that's just, it's just generally very promising, and it sort of suggests that our answers are right.